Can see everything, right? All right.
Looks good.
Perfect. Okay. Thank you for the introduction. And so I have added something to the title because we have started working on something else that is related to antineutrino studies. So now it, besides showing you the effect of uranium-238 fission yields, I will talk about the effect of isomeric yields, which we have been studying for the past 6-7 months. So in this talk, I will, well, first give some background. What is the antineutrino anomaly? What is the bump? And how do fission yields start to play a role in reactor antineutrino predictions? I will introduce the case of uranium-238 and how we have tried to use fission yield measure with new techniques and inverse kinematics that have been published to study how these measurements affect the antineutrino spectrum produced by uranium-238. And then I will move to what we've been doing lately, that is looking at another piece of the puzzle of reactor antineutrino issues, that is the role of isomeric yields on the antineutrino spectrum. We'll present something like that, something about that, and then move to what we have planned for the future related to fission yields. So, well, fission yields, everything started with fission. And since a lot of this work is related to applications, we generally think of an actinide that is fissioning after a neutron is absorbed. So the actinide will absorb a neutron and will start deforming, and two fission fragments are produced. These fission fragments are highly excited. We start de-exciting by emission of neutrons and gamma. And because they are produced from much heavier nucleus, they will uh, find themselves with an excess of neutrons and will then populate the sort of neutron-rich side of the charter nuclides and be beta unstable. So that we start to beta decay towards the value of stability, and that is uh, sort of what we have in the core of a nuclear reactor. And if we think of a nuclear power plant, so what we are interested in is, of course, to produce energy. And if we look at how this energy is distributed in a fission event, we have that the majority of it is coming from the kinetic energy of the fission fragments. That is the main source of the heat that is used to produce electricity. And then we have a fraction that comes from the decay of the fission products. So we have emission of electrons by beta decay, gammas by gamma de-excitation, neutrons by delayed neutron emission. And this is something that has also, well, contributes to the energy production, but it's also something that has to be taken care of if we look at spent nuclear fuel, or the case of loss of flow accidents, or um, emergency shutdown of reactors where the cooling has to go on for a few days because of this decay heat coming from the beta decay of the fission fragment. Then another fraction that is not directly but still interesting for application is the excitation energy that, as I said before, produces neutrons, and these neutrons are of course fundamental for keeping up the chain reaction in the core of the nuclear reactor. Something that is absolutely unconsequential for application is the energy fraction that is lost to antineutrinos, because this does not release any energy inside the core. But nevertheless, this makes nuclear reactors as a huge source of antineutrinos that we'll see has been exploited since the beginning of studies of antineutrinos. So if we think of two fission products, each of them decaying on average 3 times through beta decay, we have 6 antineutrinos per fission. And then if we have like a nuclear reactor with a 1 gigawatt electrical power, we have about 10 to the 20 fission. So we have like more than 10 to the 20 antineutrinos per second produced in a nuclear power plant. And this is what was used. And if we look at, of course, the distribution is very uneven because it's, of course, concentrated where nuclear reactor are operating. And this was the first source that was used in 1957 to observe neutrinos for the first time. And fast forwarding like 50, 60 years, now antineutrino, well, nuclear reactors are being considered and being used as a source of antineutrino. The reason is that the fact that we produce, like they're produced by a beta decay, makes them like a pure source of only electron antineutrinos, which is ideal for oscillation studies. So as part of the sort of work towards the understanding of antineutrinos, a lot of experiments started to being designed in the first decade of the 2000s. And one of the experiments that started looking at one of the mixing angles that can be addressed with antineutrino from nuclear reactors is the diabase experiment. This is one of the so-called short baseline experiments because the detectors are placed just a few hundred meters from the source that produces the antineutrino. So they went on with experiments, they started publishing data, they published the mixing angle, but what they observed that was not expected is what has been dubbed the antineutrino anomaly, that is basically a lack of antineutrino compared to predictions. Not only that, but they also observe a deformation in the shape of the spectrum that appeared around 4 to 6 MeV. And this was confirmed by further experiments of the same kind, still short baseline reactor-based experiments at Reno and Double Shoe that observed this missing antineutrinos and this excess between 4 and 6 MeV that we call the bump. So, okay, now we have missing antineutrinos and an excess between 4 and 6 MeV, like compared to predictions. How are these predictions made? So there are two main methods. One is the conversion method that starts from um, measurements of the integrated beta spectrum from the decay of fission fragments. There was an experiment that was performed in the 80s at ILL using a thermal reactor flux and looked at the beta spectrum produced from all the sort of major fissile actinides that are in the nuclear reactor core. This conversion method was improved in 2011 by Huber and Müller that combined this experimental information with information coming from the databases. And this is sort of now the golden standard for antineutrino predictions. So that's what are the predictions earlier referred to. Then we have another method that is the summation method that as a nuclear data person is the one I will be mostly focusing on, and that uses, as the name suggests, decay data and sums the contribution of each fission product to this antineutrino spectrum. So we have an beta and antineutrino spectrum from each fission product, and then the fission yields, that is the probability of producing a particular fission product, will weigh how much this beta and antineutrino spectrum contributes to the final total antineutrino spectrum. An issue with this, however, is that we have much larger uncertainties than the conversion method because we are summing values that have a large uncertainty in some cases to begin with. And we don't have the leading uncertainty comes from experiment. That's the case of the conversion method. Why do we talk about it is because for uranium-238, there is no data coming from this thermal irradiation because uranium-238 fissions at fast neutron energies and not at thermal energies. And on top of that, so there exists experiment of the beta spectrum, but not at the same precision that was reached with the ILL spectrometer. So like it makes sense to work on a summation method calculation for uranium-238. Even more so because for the fact that uranium-238 produces more neutron-rich fission products, it is um, this creates a harder spectrum of antineutrinos, so at higher energies, which convoluted with the cross-section of inverse beta decay, that is the process that is used in these experiments, is sort of dominating in the higher energy region. So this uranium-238 only contributes for 10% of the uh, total number of fissions in a nuclear reactor, but experiments with highly enriched uranium fuels did not exclude the possibility that something else other than 235 could contribute to the bomb. And that's where we are now. So uranium-238 seems to be possibly responsible for this bump, and that's what we are trying to explore. Now, if we look at the data that we have, is the nuclear data library and the fission yield sublibrary of the data library. If we look at the NDFB, this is work that dates back to the work by England and Ryder that was developed in the 80s. But even if we go to Europe, where there is a much more recent release of fission yield information that was coming out in 2017, this did not include any new experimental data for uranium-238 compared to the earlier release that was done more than 20 years ago. On top of that, if we add to this the fact that most, if not all, of the isomeric yield ratios are coming from a model that was developed in the 70s, this is something that needs work if one wants to include or use nuclear data libraries and fission yield libraries for this kind of calculation. And here is where we come in. So when I started working at Brookhaven, the goal was to, starting with uranium-238, start compiling all the experimental data that have been measured since basically the beginning of time. So we went out looking at papers, databases, we got the data, we updated them whenever possible using the latest decay data information coming from NSTEF, and we archived them all in a database that we could use for this kind of study. And looking at the evolution of the data, so what we have is that, well, of course, we have more data now than we had 30, 40 years ago, but it is also interesting to see that new techniques are changing the kind of information that we have. So if we look at the earlier experimental determination of fission yields that was happening up until the 2000 or like even earlier than that, what was measured was generally beta decay or gamma decay that was was done hours, days, sometimes even weeks after the fission event, which meant that what was measured was the amount of a fission product with all the contribution from precursors. So what we refer to as the cumulative fission yield, that is this blue curve. Now, with time, with development of new experimental capabilities, what has been done is to try to move closer and closer towards the moment of fission. So much faster gamma ray spectroscopy that maybe doesn't need the chemical separation, and the use of much more advanced detector systems, such as systems in inverse kinematics. And what we see here is that this jump that you see in 2019 all come from independent yields that were measured in one single experiment. That is the based on the Vamos spectrometer Ganil. So if you look at when the earlier evaluation were done, sometime in the 80s or 2000, so most of the determination of the independent yields were based on some sort of theory because there was not enough data to sort of cover all fission product. And this has changed now thanks to the use of inverse kinematics and the results of this experiment. So what we have done is like, okay, we have new data. We don't have an evaluation yet, but this will take time. So let's try to see how this new data will affect the antineutrino spectrum. And this is sort of what we have tried. We've tried with two experiments that are both done in inverse kinematics. The one is the Vamos and Ganil that was published in 2019. looks at a compound nucleus 239 uranium with an excitation energy of about 8 MeV, which is extremely close to the system that we would find in the core of the nuclear reactor when we have fast fission of uranium-238. And we looked at SOFIA experiment GSI that looks at a slightly different compound nucleus with 238 uranium at 15 MeV excitation energy. I will skip through all the steps that went from going from the independent fission yields to the antineutrino spectrum, and I will show you only the result. That is, we see no bumps. So if we compare the new independent fission yields and we sort of apply the summation method with starting with this independent fission yields, and we compare this with the independent fission yields in Jeff, we see that basically there is no effect in the bump region. And this is one of the curves that we obtain. We try to constrain the independent yields with the much higher precision cumulative yields that would give us the mass distribution. Still, this didn't change, and the same happened for the SOFIA results. So is this the end of how we can work through this antineutrino bump issue? Is, well, of course not, because I've already introduced what I'm going to talk about. So of course there is another part of the work, that is, let's try to see how isomers and isomeric yield ratios influence this antineutrino spectrum. So what we have is that of the fission products that are produced, of the hundreds of fission products, we have about 200 with the isomer that is known to exist and is long-lived enough to be relevant for applications and to be included in the nuclear data libraries. Some of them, of course, will decay by internal transition. Some other will decay by beta decay. And when we produce the nuclear data library, the evaluation in the nuclear data library for fission yields, we need to assign what is the probability of fission ending up populating the isomer or the ground state. And we define this as this isomeric yield ratio, that in this case, of course, we can define in many ways. One way is to take the isomer and divide by the yield of the isomer divided by the total yield of the isotope we're looking at. Now, how does this affect the antineutrino spectrum? Well, the decay from this, when this isomer decay via beta decay, they will populate different levels in the daughter nucleus, and this will result in different branches with different shapes of the beta and antineutrino coming out of the decay. So by changing the isomeric yield, we change the weight of each of these two possible states and these two possible shapes. And this can affect the total shape of antineutrinos. On even more so, if we look at the fact that only a few nuclei, only a few isotopes contribute in the energy range that we care about, that is this 5 like center around 5 MeV. So we have only this few color line seem to contribute the most in this energy range, and many of them have isomers that have to be determined. So what we do, once again, we start compiling experimental data. We found data for 56 fission products. Now, incidentally, they're not available for all fissioning systems. So what the assumption that is generally done here is that whatever is measured for a fissioning system can be extrapolated to others, with assuming that there is no dependence on the compound nucleus and only a slight dependence on the energy, the excitation energy of the system. So this is so we looked at more data, and this is compared to, as I said, a model that was used and developed 40 years ago to predict isomeric yield ratios. And this is still the model and the theoretical calculation that is used in all evaluated nuclear data libraries. And this is what all the isomers that you have in the libraries are based on. So if we look once again at the distribution of how much data we have, we were about here when Madeline England developed their model. Now we are 5 times more experimental data points. And even in this case, we have new techniques that are being applied to the measurement of isomeric ratios. One of them is using a penning trap, and this work that I've been involved in when I was doing my PhD in Uppsala. We were measuring isomeric yield ratios at the G-Filtrap penning trap in Jyväskylä in Finland. So one of the so a penning trap is basically a high resolution mass spectrometer that is able to distinguish the levels between the isomer and the ground state based on the mass. So what is, we started working on this, trying to use it for fission yield determination. We ended up like working a lot with isomers because a lot of the dependencies on Z and A are sort of taken care of because we're looking at the same element with the same mass. So all the problems of efficiency depending on Z and A sort of cancel out in this case. And this is a great way to access a lot of the quick isomers that have a very short half-life and whose precursors have a very short half-life, for which it is hard to determine the independent yield ratio. So on top of that, there is no need for extensive decay data or any need to measure any decay radiation. And this allowed to measure fission products whose isomers had never been observed before. And this is data that has been coming out since 2018 and is coming out more, and there's more experiments coming even from other groups. So our work when we started this is like, okay, now we have so much more data. What can we do with it? Can we improve the Madeline-England model? And this is how we started. So we started analyzing what have they done and can we sort of replicate what they have done, just improving the model using the extra data that we got. So the Madeline-England model is something that, well, Madeline England, they like studying from Salamos, they were producing this evaluation of fission yields, and they needed a way to obtain all isomeric yield ratios for known isomers. So they did not have a lot of data, so they decided to develop a model that is that requires minimal information. They knew it was rough, but that's what they had, and that's sort of almost what we have right now. So what this is based on is by knowing this model, by knowing the spin of the ground state in the isomer, they assume a statistical distribution of the probability of the initial fragment to have a particular spin, and they say those spin that are closer, so they identify a cutoff spin. Those spin that are closer to the higher spin will populate the higher spin state, and those that are closer to the lower spin will populate the lower spin space. And that's all the model sort of predicts. So there is no more nuclear structure into this because for many of these fission products, it was not known at the time, and for some of them it's not known even today. So they have one parameter in this model that is the one that defines the shape of this distribution, of this probability of populating the J. And what they did was to fit this to the few available data that they had that was concentrated in the heavy mass region. And they say, okay, we will extrapolate this to all other fission products because that's what we have right now. So we knew it was rough, and our hope was that with more data, we would have been able to give a much more precise description of this GRMS parameter that would allow us to predict more accurately the spin, still based on the Madeleine-Ingram model. That is, as I said, still being used today in the latest release of the Fission library of Jeff 3.3. While we were writing up this and it was in the hands of the referee, then this article was published on Nature that talks and discusses the generation of angular momentum in fission. And the work by Wilson they measure the spin of the fission fragments, and they reach the conclusion that, not depending on the fissioning system, which is good because that's been our assumption all along, they can parameterize the spin as a function of the mass with a simple function. So the spin will follow a sawtooth that is similar to the gamma multiplicity sawtooth, similar to the neutron emission sawtooth. So what we did at this point is like, okay, we have experimental data, we have a model, let's try to work our way around and try to deduce the GRMS from the ratio, from the isomeric year ratios. This is what we did. And our idea was, if this model is correct, what we will obtain is a reproduction of the shape that Wilson has measured. We did this, and well, this didn't work exactly as expected. So we knew that the assumption that is made today, that is that there is a constant GRMS for all fission fragments, is wrong. It's too simplified. What we were hoping is that the GRMS extracted from experiments using the Madeleine-Ingram model would follow this sawtooth distribution, but the spread is too large to allow us to still use like a more advanced description or parameterization of the GRMS that is the only parameter of the model in order for us to start predicting. So it's not even worth including this GRMS because it will not make anything more precise. So what we are left, if we go back to the antineutrino and the bump, the study of the effect on the bump, what we have is that for uranium-235, we have about 107 isotopes that we need an isomer for. So we need 170 isomeric yield ratios. And we have something that is basically just no better than a poll in an election. And what is more is that we can only have an election in 40 of these 170 isotopes because we only have experimental data for that, for 40 of them. And in many cases, if we look at, I just rank them by color, where like the red one is where the isomer takes the largest share of the yield, and the blue where the ground state takes the largest share of the yield. In many cases, the prediction will actually give us an opposite share. So it's a model that is not really great. So, but this is all we have so far. So what we did was we took all our recommended experimental yields that we just published, and we tried to complement that with whatever is in the Madeleine-Ingram model. So we changed 42 of the ratios, of which half changed consistently, like quite consistently, like compared to the initial value of the Madeleine-Ingram model. And what we did was to compare the antineutrino spectrum produced by using these ratios. And what we have, and this is something that we just started, so we are working, like as these days we're working on this. What I show here is the ratio of the antineutrino spectrum obtained with the modified Jeff 3.3 yields, introducing the recommended yield ratios over the original Jeff 3.3. And what we see is that, oh, wow, we have a change in the bump region, and we have a huge change around 8 MeV. And if we study where these are from, these are just or mostly contributed from two fission products, one that is C296 and one that is C298. This is because of the large yield and large Q value. And in case of V298, it's one of the isotopes that would flip from being majority isomer in the Madden-England model and majority ground state in the experimental data. One word of caution is that E296 has not been measured, or we did not find values for low energy neutron-induced fission. So what we based our value on are measurements of proton-induced fission at 25 MeV that are coming from penning-drop measurement. So whenever data will be available from spontaneous fission or low energy fission, this is something that would really add to the conclusion of this spectrum. As of now, what we're doing is trying to look at some sort of changing the values of all the other isomeric yield ratios that we did change and we were not able to change, to study what is the effect on the antineutrino spectrum and try to identify the few fission products that we expect that will contribute the most to the spectrum in the bump region. And this is basically all the work that we have done. What we are planning to do, and we are starting right now in these coming weeks, is trying to measure something. And what we are doing is to still having in mind the fact that no fission yield measurement is possible with, no accurate determination is possible without accurate nuclear data. We are going back and remeasuring some decay data for some particular fission products. We have found that especially some for applications, and especially application for the CTBT, that is the Comprehensive Test Ban Treaty, that is this treaty that monitors for unauthorized use of nuclear weapons. There are a few radionuclides that are in need of new nuclear data. So what we are doing is we cross-checked this list from the CTBT with NSDAF evaluations and try to find those that can be measured and are in need to be measured. So the plan that we have now for this summer is really something that is going to happen in a couple of months from now, is measure 3 particular fission products, Iodine-130, Lanthanum-140, Cerium-143, and they're all sort of intended to be used, this new nuclear data intended to be used for nuclear forensics. So to try to gain information in different ways on the initial nuclear event based on the kind of on the yield of these fission products. And this is all I have. So I would like to thank the funding agencies, my supervisors and colleagues at Brookhaven National Lab, and students that worked on this, people in Uppsala that have supervised me and worked with me, and people at Jyväskylä that work with the penning-drop. And that is the summary.
Okay, thank you very much for this very nice talk. We have time for questions. Please enjoy your virtual applause. Who wants to go first? You can raise your hand, you can put questions in the chat, you can unmute yourself and ask the question, or you want me to start first, then I can do that. I was wondering about the inverse kinematics experiments to measure fission yields, because the excitation energy is very different than in a reactor, no?
Right. Well,
so how do you correct for the effect that this might have also for isomer production?
Right. So one thing to say is that these experiments are not actually sensitive to isomers. Yeah. So they will only measure the independent yields. So they have no, they're not able to distinguish if there is no further determination. The excitation energy is not in, it's actually not that far for this case, because we are looking at, so we have, if we have uranium-239 compound obtained with the neutron capture. We have a threshold around 1 something MeV,
Yeah.
and then we have the neutron separation energy. So we reach levels that are very much similar to this 8.3. Here we have a we have a spread of a few MeV, but the excitation energy, at least in this case, is not entirely different. With Sophia, we actually see a much different shape of the mass distribution. So we have, I think I have the right. I don't know how to access that. I will need to. The mass distributions are like much more similar to fast neutron-induced fission. The Sophia is the green one. It's a messy plot, but you see here in the symmetric region is like this is fast fission. It's like the symmetric fission is like enhanced compared to the standard modes.
Okay, very nice. Thank you. Questions? Augusto, please.
Yeah, thank you very much. Very nice. Following on Alex's question, I agree that the excitation energy probably is fine, but the spin distribution must be much different.
Yes, this is something. I mean, I know what I read, so I don't really can vouch for much more. But is what has been observed in this kind of experiments is that this surrogate reaction, at least when it comes to production of independent yields, will produce shapes and of the fission fragments that are not so much different than what we would get from the direct reaction. That is so it seems like the yields, that is just the probability of producing particular isotopes, is not so much affected by it. And we got incredibly good results, even like just by summing the entire distribution along the A line. So those are actually great experiments that are like, of course, the final uncertainties will be larger than compared to the one that one obtains if one measures the end of chain fission yield, but the shapes, as far as we know, because then it's also like, okay, they've not really been measured before, so it's like
Sure.
there have been measurements of the light fragments, but not such a consistent measure along the all over the mass distribution.
Somehow, I mean, that okay, maybe but somehow I find it a little difficult to gauge. I mean, if you have a high spin isomer and you have high spin states being produced in the initial reaction, then you have more chances of populating that. Unless, so I don't know. I mean,
Right. Yeah.
I mean, if you break the fragments they are spinning already, you probably transfer some angular momentum also to the fragments. But
right. Then is to see how, since one measures before any of the decays, then it's like how much will this affect the actual probability of the yields. That's
And then one last comment, perhaps. There's been a lot of recent developments on the theory side, and I know my colleague here at LBNL, Jürgen Randrup, has had a lot of success with his new approach to understand yields and angular momentum. Is there any value to work with?
right. Yes. I mean, that's what we are. So what we have done so far is basically looking at the data that are there. And this is sort of the starting point to like, okay, how do we improve these models? Because we still need models we cannot measure everything. So
Sure,
we
sure.
need models for like sort of
Yeah.
how do you say? Yes. So
Well,
we need the models to
he's
sort
been
of
very
predict these
successful.
yields. And so far for the for the yields, like the yields themselves, we have what has been done from the Jeff collaboration is using models, like they moved from this Val systematics for the independent yields to the GEF model, that is the one developed by Karl Schmidt. And for what regards the isomers is something that really needs work, because also like what the Freya people have developed is something that is it's extremely valuable because it's more like the decay uses actual levels from Ripple, and but then it has to be taken the sort of extra step to give the yield ratios that we can rely on for the, because so far a lot of the models that have been developed that look at the so more complex the excitation, they all find limitations based on the like the sort of level densities and all the, so like everything has to be, so if we don't know the fission, like the properties of the fission fragments, will always be something, some limitation of the model that cannot be, even with a perfect model, one cannot sort of obtain like results that one can trust. And that's sort of the, as I see, is the, so yeah, we can move away from this simple model, but it's like, how much better will it be? And all the work that has been published so far is like, even with more advanced models, they end up getting results that in some cases are not better than this simple linear model. That's which is of course something that needs work, but it's something that is yeah.
Good. Well, thank you. Good luck.
Thank you.
Okay, next question or comment by Werner Tornau.
Yeah, I would like to comment about Sophia again. If you take the independent yields measured by Sophia and add them up to get the cumulative yield, and then compare this result with measured cumulative yields in real photon, uranium-238 fission, that looks pretty good, in fact.
Right.
And that's surprising, but it seems to be nice.
Yeah.
And another comment, of course, Sophia and Vamos, they do not measure isomeric yield ratios, right? They just measure one.
Right.
So we won't get any information on the isomeric yields from Sophia or Vamos.
Right. So what we did here was to get isomeric yield ratios from libraries. So we need, when we produce this antineutrino spectra that I showed you before, of course, what I skipped through is a lot of the steps that we need. So we need a lot more information than what we can get, because we don't have isomers, we don't have complete. So the not all fission products have been measured because some have too low of a yield. So we need to sort of provide all this information. This all come from, I mean, in our case, from the libraries. So we can maybe make some more advanced calculation. But so far it's been, we took the isomeric yield ratios from Jeff 3.3, and then we complemented with the decay data to allow the decay of the fission products. But yes, that's
yeah. I don't know whether your colleague Alejandro gave you some of the isomeric yields we did measure at 2
right.
MeV
Yes.
energy in uranium-238.
Right.
We have okay, go ahead.
No, please.
We have updated results, which I have not released yet, but they are about ready to be released.
That would be great. I'm not sure I don't think for our compilation, the one that will, I think it will be published in the next few weeks. I think we only used published results. So your
I understand.
ratios will probably not appear there, but
it shouldn't be.
We would be happy to, yeah, it should not. So we would be happy to, like, we are keeping up to date. So we have our table, like our internal tables, and we would be happy to sort of include that as soon as they are. And we will update the values.
Okay, next is Kay Kolos and then Anton Tonchev.
Thank you, Alex. Hi, Andrea.
Hi.
A really nice talk. So I actually have a question. You might have elaborated on this, maybe I missed the measurements at the end that you mentioned that you're going to do for nuclear forensics. I guess I'm just interested to know how does the priority list was like, you know, based upon, and what exactly are you going to measure with those 3 isotopes that is of interest to
all right. So
forensics?
yeah, I was very quick here. So what we are trying to remeasure is decay, like gamma intensities. So we're trying to reconstruct the decay scheme of these 3 isotopes.
Mm-hmm. And did you just, you know, just by kind of looking at the masses that that you chose, do you have like, would you be able to elaborate how those specific isotopes or masses were chosen? Did you guys, I don't know, collaborate with nuclear, I guess, forensics?
So yeah,
scientists?
so what we did was like, okay, we looked at the list of the nuclear forensics that were like, so what isotopes are being used, and then we looked at, okay, what is in NSDF and what needs to be remeasured, and then is what can be remeasured with for example, gamma sphere. Like so we tried to sort of cross-reference all these lists and then try to find a few cases that might be in need of remeasuring. Some of them that now we're trying to figure, like, okay, we have figured out how to produce all of them so that we can actually measure them properly. And that's so it was a mix of what is interesting, what has not been, where nuclear data could use improvement, and what can be measured. So it's all this at the same time. So in case of Xenon-135, iodine-135, it would be hard to do it with like to produce the sources. So what we asked for was like a caribou beam that would allow us to measure the decay of one and the other. So it's all like a sort of combination of all this. I don't know if I answered.
Yeah, that's
Right.
great. Thank you.
Okay, and
Anton?
then Anton.
Hi, it's a very nice and useful presentation and work. I have a comment first and question. The comment is about the inverse kinematics and direct neutron-induced fission comparison. As you know, in inverse kinematics, and it was already mentioned, you have even if you have the same compound nucleus from which you fission, even with close excitation energy, you have different angular momentum involved. But just to confirm what you just also said is that here at Tunnel and at Livermore, we did a measurements at using monoenergetic neutron beams on plutonium-239 and compare the photofission product yields from plutonium-240 at high intensity gamma ray source facility. So you use the real photons instead of virtual photons like inverse kinematics, but matching the same excitation energy on the compound 240 plutonium. And it turned out that the fission yield distribution and the absolute yield and distribution are phenomenally very close. So that means Bohr hypothesis works, what these nature people claim too. When you split the nucleus, they forgot how it was produced, right, etc. So this is about to be published soon, and I will keep you updated on that. Yes. And my question is, in the fission yield deficiencies and the so-called bump appears only when you compare the theoretical predictions with the experimental data. Right?
Right.
So, and now, even if you use the new data and Jeff data, I think you say does not support the bump. And my question, whether the two issues, the deficiency and the bump, are related or just independent or just artifacts?
All right. Okay, I see what I think. You correct me if I understood wrong. So like these two effects, there is like this deficiency of the sort of like total integral number of antineutrinos, and then there is the shape effect. So they're two
Right.
different things that can be, yes, they can be due to the two different things. Now, the issue is that the summation method is, I think it will hardly give us thing precise enough to say anything about the total effect on the antineutrino spectrum, so the total number. So what we are looking at with the summation method is mostly the effect on the shape, because there we have, like, we can say, okay, if we compare just the two different libraries or two different summation predictions, do we see any difference? And that's what we're trying to do. So we are focusing on the bump because it's something that does not necessarily need to have like a sum that will precisely give us the total number, the total flux of antineutrinos. So that's why most of my discussion has been focusing on the bump, because it's what we think we could contribute to with the summation method, because of the larger uncertainties that come from the method itself. So we don't have any high precision measurement that would sort of, where the uncertainty would sort of dominate or like be reduced.
Okay, and maybe a comment, but you mentioned in one of the last slides that of course we know that there are two issues in these two issues, that is the yields and the beta spectra, right? And the deficiency of the data, obviously, that's what drives probably this deficiency and the bumps. But it seems to me, and now we are focused and we have an extensive study here at Livermore, Los Alamos, and Tunnel to study these cumulative yields. And I'm glad that you also focus on that. But I think even bigger issue is the beta decay spectra. That is something, I don't know, experimentally, it's not addressing. It's difficult to measure in absolute way, as with high precision, say better than 10%. But that is something which will be always a part of the equation. And you cannot solve the problem without that part too, isn't it?
Right. Yes. It's I mean, a lot of the unknowns come from the beta decay spectrum, from the shapes and from the, like, yeah, I agree. It's
and
just
that might
that
be even bigger unknown.
Yeah, I think what is from my point of view, I mean, I come from a sort of fission yield kind of background, so for me it's like, okay, we have fission yields that need to be measured for applications, and we can use this for theoretical studies, which is kind of exciting for this kind of research. So we have something that can find applications in nuclear forensics or non-proliferation or nuclear reactor physics, and then we use it for a sort of basic research that is exciting, and that's sort of where we're going. But I agree. I mean, it's like there is a lot of pieces that need to be put together before we can solve that. Yes.
Thank you.
Okay, and the last question goes to Diego Ramos.
Hello. Hi, Andrea. Thank you for the talk. It was very nice. Congratulations. I think I saw in your, of course, I understand that the measurement of the isomeric yields is a key point and is in the top of the priority concerning the antineutrino anomaly. But still, I saw that you showed that not only uranium-238, but also like plutonium-241 and some others, they have a strong contribution to this. So we know that from the fission yields that the production for the heavy fragment region, they will be more or less the same, but for the light one, they will be rather different. So do you think that could be also interesting and important concerning the antineutrino anomaly to measure precisely those fission yields for the different for those different systems?
Right. Yes. I mean, it should be said now. I don't have like a full compilation of data as we have done with uranium-238. Generally, for thermal fission, it has been measured more often, let's say. But new data on independent yields are still scarce, because the problem is like the measurements that have been done 30 years ago were based on techniques that were developed like even 50 years ago. So like all this new these new systems that can be studied in inverse kinematics and would solve all the issues with, I mean, only having the C distribution in the low mass peak. That is something that, I mean, if it's available, yeah, it's data that are like would be great to include into the description of the nuclear data libraries, because now a lot of the independent yields in the libraries are coming from theory. So I mean, we have this theory distribution, and we sort of we accept and we believe it, but it's still that's it. So yes, I think more measurements have been or will be published on Uranium-235, I think, of the same, like 235, 236 compound or something.
Up to my knowledge, no,
Okay,
not right
maybe
now.
not. All right.
Okay, thank you very much.
Thanks.
Just if I just say a small comment about the spin population of inverse kinematics.
Right. Yes, please.
We did larger comparisons with different set of data. Of course, we cannot do comparison one by one because there is no isotopic fission yields, for instance, from neutron induced, or at least not directly measured. But up to what we can compare, we found a extremely good agreement between the inverse kinematics at low excitation energy, which also means low spin population, at least not like fusion fission, with neutron-induced data. Even checking the level scheme, the decay of the rotational bands from the fission fragments, they are so large compared with the initial angular momentum that you may populate in the system, that make kind of irrelevant the initial angular momentum that you are putting into it.
Thanks.
Okay, great. I don't see any more questions, and we have 3 o'clock. This is like a point landing in terms of timing. So if there's no urgent question anymore, then I would like to thank Andrea again for the very nice talk, and the audience for an extremely lively and ongoing discussion. That was really fun. And then I will leave you with the announcement that the next preview seminar will be in 2 weeks, and Alex Dombos from Notre Dame will be speaking, hosted by Texas A&M.